Okay, well, welcome everybody. Thank you for coming to this history talk. I'm very grateful to Joe Gersher for coming to talk to us again this quarter. Joe's a very faithful attendee at our seminars, and he has spoken several times before, so he's very much part of our history, and I really admire people who are willing to look back and read all these papers from long ago, because history gives us a certain perspective that we don't get from normal textbooks. For example, I've started to read the biography about Alan Turing, and I learned that John von Neumann, whom Joe will talk about, is the one who took the apparently different theories from Schrödinger and Heisenberg, made them more abstract, and showed that they were equivalent. I didn't know this until recently, reading this history book.
Mm-hmm.
So we'll see how John von Neumann fits into our favorite method for solving AX equals B. So
Okay.
Thank you for coming, Joe.
All right, Michael, thank you. I want to thank everybody for coming to hear me talk about the history of Gaussian elimination. When I was growing up as a student, it was always kind of a big question, who invented Gaussian elimination? And there were even people who would write papers about how Gauss invented Gaussian elimination. But if you looked in old algebra books from before Gauss, there was Gaussian elimination. So I mean, he obviously could not have invented it. There's a law, Stigler's law, which says that the thing that if somebody's named after something, or something is named after someone, then they are not the person who invented it. So that's the case with Gaussian elimination as well. So I wanted to do this once and for all. I had a very nice editor at Historia Mathematica named June Barrow Green, and I was sort of a novice at writing history papers, and she kind of helped me through it. But I insisted on telling the whole story. So I didn't want to leave anything out. It's a huge paper. You don't have to take notes, you can just read the paper, and they were kind enough to publish the whole thing. And there's also an abbreviated explanation in the notices. So there are a lot of this, is maybe interesting facts. At a certain point, it does become relevant to you if you're looking forward to a career in science or computing, and I hope I mention that part when I get to it. So roughly, what is Gaussian elimination? Well, as far as I'm concerned, it's this. It's reducing to, I think mathematicians call this echelon form or something like that. We call it triangular form. And then there's a back substitution phase. Now, most of the time it will not look like this. So you have to think, what does it really mean to have an algorithm or some mathematical concept? It's not going to look like symbolic algebra. It won't be written in equations. It'll, even today, right? We almost never look at it this way. So you have this sort of nebulous concept of Gaussian elimination. It's the same thing through history, but you have to recognize it differently each time. In a nutshell, basically there are three steps in the history of the subject. The first one was it was really invented to be an exercise in algebra textbooks. So the kind of thing, I remember learning Gaussian elimination in middle school. Whoever writes those books 400 years ago, they were actually the ones who described Gaussian elimination first. But around 1800, when technology became more important to society and you started to have technical universities and math was used heavily in engineering and industry, then solving linear equations became very important for a technical reason. And then you had a series of altered algorithms that were designed specifically to be used by professional hand computers. And because Gauss was the first one to invent these, that's basically why it got named after him. And then finally, starting around 1930, it turned into this kind of matrix factorization algorithm that we typically learn or teach today. So I'll explain where this came from as well, and then I'm going to stop roughly at World War II. So we're going to go, from about 2 millennia worth of history here. So first, before I talk about the 3 major phases in the history, let's just deal with the Antiquity stuff. And this is actually really interesting, but it doesn't have anything to do with us, because almost none of the stuff that these people did sort of made it into the modern world and actually had an impact on the way that we do things, although they did do some things that do look like Gaussian elimination, as we'll see. The oldest writing, supposedly, is the cuneiform tablets that come from a place called Sumer, which is in modern Iraq, north of Baghdad. It's basically the Tigris and Euphrates River Valley. Interestingly enough, so this is the oldest. There might conceivably be older writing, but at least when I was studying ancient history, they told us this was it. They wrote on clay tablets, and they started on the right-hand side and went left, and does this work? Yeah. They started on the right-hand side, and they went left, and then down, and then they went to the column on the left. So you kind of think writing was probably invented by lefties, I don't know. Interestingly enough, at a certain point, enough right-handed people started writing, and then they switched it. So they started writing on the left and moving to the right. But it was so ingrained that they did the right-hand column first that they continued to do the right-hand column. I just think this is fascinating. The other interesting thing is, by the way, Arabic and Hebrew still write backwards compared to us. When they turned the page, instead of flipping it from right to left, they flipped it from top to bottom. So there's lots of different ways to write. Now, where these tablets come from, nobody, the general part of the world, but they were all, taken by antiquities dealers before modern anthropology and archaeology would do it the right way. So we really don't know where these things came from. But there's thousands of these tablets, and about 1,000 of them deal with mathematical subjects, and a few of them, very few of them, like this one, actually have math problems on them, sophisticated math problems. This was probably like a textbook or some kind of a problem set for people in whatever the equivalent of an educational system was in ancient Sumer. So here's the problem. On one of the problems, you've got 2 fields. There's a condition on the total area, and then there's a condition on the rents that are earned from the fields. It's interesting, it's a rent. So they must have had some kind of capitalist system in those days. And then there's a condition on the amount of grain that comes, or amount of rent per unit area for each field. And then you have to solve this problem. And it's also interesting that it says frequently in the text to remember this, keep it in your head. So you kind of think maybe you were supposed to do this in your head. And by the way they did this, now we would turn this into a 2x2 system of linear equations. What they did was they picked values to satisfy the first condition. So each field, they just divided the area in 2, 900 apiece. And then they looked to see what the discrepancy was, the error in the second condition. And then they derived an equation that said, well, if I adjust this one up and this one down, how much do I come closer to satisfying the second condition? So they reduced it to one condition that you could solve, and then you get the answer. You could try to solve it in your head. I sort of gave it away. It's kind of easy to do once you know. So that's it. What those people were doing, really don't have any idea. You can read history books and they'll kind of make up stuff about what they thought was being done, but no. An interesting point, by the way, is that most of the problems are not linear. most of the problems are non-linear. Like you have areas of fields and you got the dimensions of them and you want to figure out what the dimension of the field, the area of the field is. Okay, let's skip ahead a millennium and a half. This is not well motivated, but this is all the stuff there is from antiquity. So in ancient China, there were apparently a class of itinerant mathematicians, you can call them, who would solve problems. If you had some kind of a math problem, you could hire one of these people to work on it for you. And the way they solved the problems was by using something called counting rods. And if you look here, they got these little sticks right there. These are the counting rods. They're like Roman numerals. You know, 1 rod is the number 1, 2 rods is the number 2. If you put them sideways, it's a negative number. Or if you were wealthy enough, you could get a different color stick. So the white ones would be positive and the red ones would be negative. And they would arrange the sticks on a square piece of cloth. It was called a counting table, but it wasn't actually a table. It was just ruled into squares. And they would put the numbers into the boxes and then manipulate them to solve problems, okay? So this was a spreadsheet. This is like a 2,000-year-old spreadsheet. Now, the only reason we know about this stuff is because somebody around 100 BC wrote up a book called The 9 Chapters of the Mathematical Art. We don't really know who wrote that, but some years later, a mathematician named Liu Hui, is that the way you pronounce it, wrote about this 9 chapters. And the way he did it was he took the original problem set and he inserted his own comments. And so we don't really have the original anymore. We just got the commentary version or the revised version from this fellow. And then, of course, after him, many people added their own revisions. And the historians here try and figure out what was his original version, but nobody knows. The only extant example comes from about the year 1600, so it was copied many times, and whatever originals there were lost. Okay, so here's one of the problems in chapter 8. There are 18 similar problems like this. You've got sheaves of grain. You would go out to the rice field and grab a bunch of stalks, and then you would cut them off at the bottom. That's a sheaf of grain, okay? So you've got 3 sheaves from top grade rice paddies, you've got 2 sheaves from medium grade, and you've got 1 sheaf from low grade, okay? So here in the right-hand side, this 3 top grade, 2 medium grade, 1 low grade. And when you extracted the grain from the stalks, then you ended up with 39 dao of grain. And I don't know what these units are, but that's what the problem is. Then there's 2 more conditions that gives you these other columns on the counting table. Okay, so the way they solved this was by Gaussian elimination. I mean, there's essentially no other way to do it. They would fix the right-hand column, and then they would add it or subtract it to the other 2 columns in order to put zeros right here. And the way they would do this by cross-multiplying with the leading term, because they wanted to preserve integers. So you take 3 times this minus 1 times that gives you 0. And 3 times 2 minus 1 times 2 gives you 4, and so on. Okay, so now you do that with the first and the third, and also the second and the third, and then you've got zeros. Then you repeat on the smaller system to put a 0 right there. So it's Gaussian, I mean, just turn it sideways, it's Gaussian elimination. The amazing thing is, it even looks like matrices, and it's 2,000 years old. For the back solve, what they did was they actually repeated the process, putting zeros in down here. Now this wasn't Gauss-Jordan elimination, because then you would put the zeros in as you do your major reduction step. It's more efficient to do it in a back substitution form. And they also knew, by the way, that with this kind of integer multiplying, you tended to get large common divisors. And so at a certain point, they knew the right number to divide out to get to reduce the size of the integers. And then finally, you can just read off the solution. Okay. And as I say, you can read more about this. There's a whole book about it. It was recently written, and I reviewed it for the American Math Society. any questions about the Chinese, right? Now, the Chinese were just enormously far ahead of anybody else. The closest thing that we have to kind of non-geometric, purely numeric mathematical problems in the European tradition is Diophantus. And he had, again, another series of problems. And a typical Diophantine problem, there are many so-called books of Diophantus, and this is one of them. So you've got 4 numbers, and you want to find the numbers such that the sum of any 3 exceeds the 4th by a given amount for each set of 3. And the way Diophantus solved this problem was sort of not unlike the way the Sumerians had done it. You kind of invent another variable or unknown that you can derive a condition for. So the way the problems are set up is that you take the sum of all the numbers, and then each condition is the sum minus twice one of the other numbers. So that's 3 greater than the remaining number, and that's a given amount. And then if you sum these conditions, then you get a single equation, and you can solve that for the total sum. So all the Diophantine problems are like this. Nobody knows who Diophantus was. Some people infer that he lived in Alexandria, Egypt. There's absolutely no evidence for that. Some people believe that he was actually a Shi who lived about 300 AD in what would have been Damascus in those days. But again, sometimes you look in the history books for the history of mathematics, and they give you the impression that there's this wealth of information. Absolutely not. All the original text that comes from the ancient period would fit in a single filing cabinet. And the only reason you'd need a filing cabinet is because those cuneiform tablets are really big. They're about the size of a cell phone. But all we've got from Egypt are 2 pieces of papyrus, 2 papyrus scrolls. Anyway, I've talked about these 3 here, which I think are representative. And of course, the important one would be the cuneiform, because it's so old, and what the Chinese did because it was so modern looking. For Europe, the important thing was Baghdad, because they had a university there which kind of gathered a lot of the knowledge of the prior world, and eventually the Arabic tablet or scrolls made it into Western Europe. And so we learned about a lot of these things like Diophantus probably through the Arab scholars in Baghdad. In particular, Al-Khwarizmi gave us the word algorithm, and algebra was, I guess, an Arabic word that represented one of the steps in solving these types of Diophantine problems. Okay, so now let's jump to what we would call almost modern Europe. The kind of algebra, the main contribution from Western Europe, and if I were to say this to a collection of historians, I would be drawn and quartered. But when you get right down to it, as a mathematician, what the Europeans brought to it was symbolic algebra. Okay? Up until this time, it had been all written out. It had been word problems solved by word reasoning. In Renaissance Italy, they developed the use of variables to indicate quantities. What I'm showing you here is an algebra textbook from 1554 written by a Frenchman. This is a little bit unusual because he actually wrote in French. Normally the educated class would write in Latin. And here's a problem that he's going to solve. So this is Cardano. Cardano was a contemporary Italian mathematician. And here's one of Cardano's problems. So it's a little bit like the Diophantine problem. You've got 3 men and they've got money, and each of their own money plus some part of the others gives a certain amount, and how much does everybody have? Okay, so Pelletier, is that the way you pronounce that? That's the way I would, don't know. Actually, he was an interesting figure. He's mostly known as a poet, and he was a reformer. He's writing here in something called Middle French, so this isn't quite modern French. You'll notice that some of the accents are not written the way we would write them today. And he didn't like double letters, so normally this name is spelled with 2 L's, but he insisted on spelling it with 1 L. So modern French didn't quite exist, and he made it up as he went along. That may be why he wrote in French as well. So he's starting to solve this problem, and he says, okay, let the first man be R, let the second man be A, and the third man is going to be represented by this formula. So it's 31 minus, he didn't have a negative sign, the sum of the other two, R plus A, but then he does divide. He's got a fraction symbol there. And then he solves the problem the way Cardano would. This is the next. In other words, it's all written out. It's verbal reasoning. It's the kind of thing that I'm doing now, speaking to you. I'm not writing anything down or memorizing numbers or anything. And then finally and you could figure this out. I don't know what he really did, but he does get the right answer at the end. Okay, so that's the way Cardano did it 5 years earlier. But then Pelletier said, let's do it differently. Okay, so he says, let's have a variable for each person. So R for the first man, the second one is A, and the third one we're going to call B. And then here are the equations, the 3 conditions. This is for the first man's amount, the second man's amount, and the third man's amount. And then he's going to solve the problem just by combining these equations. Notice he doesn't have an equal sign, so they just wrote it out. And they didn't have plus signs, so he just put in a P. It could be that the typographer didn't have the symbol, but if he were writing a manuscript, he would have used something, don't know. And then it looks a little bit wordy here, but that's because he's explaining what the steps are. But in each case, he derives another equation, and then he's got a little explanation for how he did it. So this is what he did, okay? So far as I know, this is the first time that anybody solved a problem like this just completely symbolically. And the interesting thing is he didn't do it the right way. I mean, look how many steps it took him. It took him 10 steps, whereas you should be able to do this in 3 steps. But it was the first time. 4 years later, there was another Frenchman, Jean Burrell, who lived near Paris, and he wrote in Latin, which would be more common at the time. And he solved a similar problem. Here's the equations that he wrote down. It's 3 times A plus 1 times B. Notice it doesn't seem to have the plus sign at all, plus 1 times C. And then this kind of bracket is his equal sign, and it's equal number on the right-hand side. And then he solves this as we would, or as the Chinese did. He does cross-multiplying to preserve integers, and he reduces the first and the second, and then the first and the third to get 2 equations that don't have the R variable. And then he finally reduces those 2 to 1. So this was the earliest example of a 3x3 system that is really solved in the Western world the way the Chinese had done it. And I think probably there was no influence from China here, because, I mean, why would this guy get a letter, I'm the emperor of China, by the way, you should solve this problem. This didn't happen, right? So it probably was independently invented. And the interesting thing about it is how fast it happened. Cardano did it verbally in 1545, and here in 1560, it's already completely symbolic. It happened really fast. Okay, so after this period that we've just been talking about for about 100 years, there were a lot of algebra books published in Europe, but most of them didn't have any linear problems in them. Only 4 of these books had these systems of linear equations. So again, like the Sumerians, the linear problems didn't necessarily come first. It was the nonlinear problems that actually they were interested in solving. All right, so that's kind of like the modern world in mathematics begins with Isaac Newton. He was a bright guy who was a distant relative of a noble family in England. So when he got to Cambridge and got to be a professor at a fairly early age, apparently somebody paid to have a picture painted of him. It's very unusual to find an image of anybody who lived this long ago. So we're really lucky to have this picture of Newton. He was a good-looking guy. And this is, now I'm going to waste a lot of time talking about Newton because he's so important. And it's a good story. What happened was all of Newton's papers got put into Cambridge University Library, and a man named Whiteside, because Newton was so important, edited all the papers and printed them. So you can go to the Stanford Library, look for the Math Papers of Isaac Newton by Whiteside, and it's about 12 volumes. And I had to go through there and find the math papers that discuss these kinds of algebra problems. And what I learned, and there's also a lot of other stuff from Newton, and this is what I learned. Okay, when Newton got promoted to be a professor, he taught algebra for 11 years. And a man in London by the name of Collins went to Newton and said, I have a plan to publish an algebra book, and I want you to edit the book because you're a professor at Cambridge, and to make sure that it's good. So the man, Mr. Collins, he actually got a book that was written in Dutch by a man named Kinkhausen. I'm probably not pronouncing that right. It's a long Dutch name. And he had it translated from Dutch into Latin, and then Collins gave the manuscript to Newton, who was supposed to revise it. Now, unfortunately for Mr. Collins, Newton was anal retentive. He didn't publish anything, and he was a perfectionist. He just wouldn't let it go from his hands. So this project dragged on for a long time, and the book was never published. Meanwhile, Newton himself started writing his own algebra book, which was never published. Among the papers that Newton wrote and sent back to Collins, there's a comment in English that says, you know, I'm reading this book, and the problem is it never tells you how to solve the problem. I mean, it's got all these different exercises, and it tells you what plus signs and equal signs are, but it never tells you how do you solve the problem. So he said, what I'm going to do is to add an actual lesson for solving systems of equations. Okay? And then what happened was that Newton wrote a third book that made him instantly famous, and that was his famous book about the laws of motion. So the king came to Cambridge and knighted Newton. He became Sir Isaac Newton, and the king gave him a really cushy job running the mint in London. Newton gave all of his papers to the university, went to London, and never worked on this stuff again. But the university was thinking, you know, we've got Newton's papers, and there's 2 algebra books there that are mostly finished. So if we join them together, we can publish an algebra book in the name of Isaac Newton, the most famous scientist in the world, and we, the university, will make a lot of money. Okay, well, Newton was really upset about that because he didn't like to see anything published. In particular, an old algebra book, when he was known for science and motion and action and reaction, was, you know, sort of indicating that maybe he was in his dotage and he wasn't really doing good work anymore. So he fought the university in publishing the book. And what happened at the end was, the resolution was, the university got to publish the book, but they didn't put Newton's name on it. So here's the title page, and you'll see the librarian there, you know, indicated this is Sir Isaac Newton's book, but his name isn't on the title page anywhere. And somewhere in the introduction it says these are notes from Newton's coursework. So this is Newton's lesson. The book was published, do I have it here? The book was published first in Latin and then in English in 1720. So this is the English version. And this is his lesson for solving systems of equations. And he says what you're supposed to do is to take the equations in pairs, if there are more than 2 of them, and you combine 2 equations to eliminate one of the variables. And you are to know, so the idea is you fix one equation and combine it with each of the others. And you are to know, where does he say that? And you are to know that by each equation, one unknown quantity may be taken away, and consequently, when there are as many equations as unknown quantities, he thought about that, all at length may be reduced to 1. in which there is only one quantity unknown. Okay, so that was the first, so far as I know, the first lesson statement for Gaussian elimination. And actually, he wasn't solving only linear equations, because this works for nonlinear too, and Newton was no dummy. He probably faced more nonlinear problems in his scientific work than linear ones. So Newton's book was a hit. And of course, what textbook writers do is they all copy from the best book. So after Newton, in all the British textbooks, you can see artifacts of his work. And what for simultaneous equations you saw was first a collection of rules for how to eliminate a variable from two equations. And Newton had substitution, which meant you solve for the variable in one equation and then you substitute the value in the other, or the formula. Then there was equality of values. That meant you solve for the variable in both equations and then you set the formulas equal with the common variable dropped out. And then later on, the addition and subtraction came up. But Newton didn't really emphasize this because, remember, he was interested in the nonlinear case as well. And then Newton's always has a rule for what to do if there's more than, these are for two equations, if there's more than two. And Newton stated recursion. A lot of the later textbooks would give explicit instructions, like, okay, if there are three, then combine the first and the second and the first and the third, and then combine the second and the third. But those books are kind of like for dummies, I guess. And then the really interesting thing is that Newton called this extermination. It was the extermination of variables. And in his Latin notes, in Newton's own hand, he originally called it elimination. And then he went back and he crossed out elimination and he wrote in the extermino, the Latin word for exterminate. So you can always tell when it comes from Newton because it's called extermination, not elimination. And so once Newton started once these books by Newton's were published, then all the other textbook writers in England started to use this lesson. And I'm not going to go, I mean, there's dozens and dozens of these things. I'll just show you a couple examples to demonstrate that I'm not lying here and they really were there. Here's Simpson. This is the Simpson of Simpson rule. There's no picture of him. Okay, he didn't belong to a noble family. He wasn't a famous professor at Cambridge, so nobody ever painted a picture of Simpson. We don't know what he looked like. But he wrote this early algebra textbook that went to 7 editions over a period of 60 or 70 years. It was a very popular textbook. And here he's got Newton's lesson. He calls it extermination. And Simpson added the idea of combining equations by adding or subtracting them, so that the Chinese approach. Now, in France, it was done a little bit differently. Whereas England had all these entrepreneurs who were writing textbooks, in France, there was in the major city, there was a royal academy. Okay, so that was for all the learned people who got appointed to this. And they would pick some guy in the academy who would write the textbook that would be used throughout France. And Sylvester Lacroix, around 1800, was the chosen guy. He actually wrote a textbook on calculus, which was very famous and much used. And he wrote a book on algebra as well. And here he's got his equations, or his lesson. Now, Lacroix did something different. He liked to have very polished textbooks, and according to him, he wanted to have, the lesson, and then he wanted a pithy name for it. And so he said, this operation by which we remove variables is called elimination. And it was from this period that all the textbooks writers started using elimination, because this was the main French textbook. And everybody in the world copied the French textbooks. They were the leading scientific country at the time. In fact, the first American algebra textbook was a translation of this by a professor at Harvard around 1812, a man named Farrar. Okay, so that was it. That's where, when you learn in middle school, I remember when I learned Gaussian elimination, it's a direct descendant, because all the textbooks just copy, of this one lesson that Isaac Newton wrote in 1720. But by the 1800s, as I say, technology was becoming important, and science was needed to make sense out of all this new knowledge. So you started to see professional methods for calculating being developed. And the most famous of these was Gauss. And now I'm going to try and go through this a little bit fast because other people have talked about this. And there's so much to talk about with Gauss, you can get lost in it. So there was a Sicilian astronomer who discovered the asteroid, or what do they call it, minor planet, I guess, Ceres. And then the Earth moved in its orbit, and Ceres was only, quote, visible, unquote, during the day, so you couldn't see it anymore. So everybody had to wait a year for the planets to align so you could look for it again. And the question was, will we be able to find it a second time? So Piazzi's observations were published in Astronomische Nachrichten, which was one of the earliest independent journals for astronomy. And Gauss, who was at that time a student at the University of Göttingen, he was roughly a postdoc by then, started working on trying to predict the orbit of this planet. Now, he was already a very accomplished mathematician. He had done basically all of his work in pure math by this point when he was in his mid-20s. And he thought, I'm not going to get anywhere being a pure mathematician. I better start wondering what I'm going to do for the rest of my life. So he started working in astronomy, and he predicted where to find Ceres. So how did he find it? Well, he wouldn't tell anybody, okay, because it was a gold mine. Every time they saw something in the sky, they would send the numbers to to Gauss, and he would predict the orbit. But he wouldn't tell people how he did it, because then he'd be out of the loop. So Gauss didn't publish his results or actually his mathematical methods for about a decade. And in the meantime, another very accomplished mathematician named Legendre in France apparently independently duplicated some of what Gauss was thinking about. And what Legendre invented was the method of least squares. He is the one who gave it the name. This is an amazing paper. I didn't write down where it actually, New Methods, 1805. He basically invents what we would call the general linear model. So you have some kind of a nonlinear equation that describes a physical problem. It's got parameters in it. You sort of know values for the parameters, but you don't know the best values. And then you've got a lot of experimental data. So you linearize the equation around the values of your guesstimated parameters. And then you substitute your observed data into the equation. And for each observation, you get a linear equation for perturbations to the parametric values. And then you have this huge overdetermined system, and you want to solve it somehow. And that's the one that you want to solve by the method of least squares. So what Legendre did was he just formed the sum of squares, and then he differentiated them by the variables. And these would be the perturbations to the parameters. And now you've got n equations and n unknowns, and you could solve that just the way we would. These are the normal equations. So that's what Legendre did in this amazingly short article. So when Gauss finally published his results, he reformulated the problem. He stated it in a somewhat different way. So I'm going to go through how Gauss did that, because he's famous for having invented the method. So let's forget about the original nonlinear problem. So we've got everything linearized, and what we end up with is this big system of linear equations. And this is the way Gauss wrote it in those days. You didn't have subscripts, you only had primes. So this ran out of gas pretty soon. And this is actually from his paper. I mean, he's got 3 equations. He wasn't going to write 3 primes. And he just said, there's a lot more down here. Okay, then here's the sum of squares. These are the residuals. And then he introduced this notation. It looks like an inner product. He didn't give it a name. Maybe that's where the inner product comes from, I don't know, which was the sum of coefficients, you know, with increasing primes. And then he restated the normal equations using these inner product symbols, these Gauss bracket symbols. And he restated the sum of squares as well. So here he wrote it all out. And then what Gauss said was, he basically completed the square. So he said, let's form this linear equation here, or this linear formula that contains p and all the coefficients in which p appears in the sum of squares. And then he invented a new bracket. It's kind of a Schur complement formula. And he said, look, if I subtract a squared off from my sum of squares, then I get something that looks exactly the same. He just completed the square, except it doesn't have the variable p in it anymore. Okay, and it took me a long time to figure this out because this is all Latin. And I'll tell you, first I read Pete Stewart's translation, and it just was not helpful at all because he didn't understand what Gauss was doing. So to get this far and to figure out what Gauss was doing was pretty rough for me. So then Gauss said, all right, let's just iterate on this. Let's invent more of these bracket symbols, and we'll invent more of these some linear combinations of variables, each one with one less variable. And basically what we're doing is expressing omega as a sum of perfect squares, and then there's a constant remainder. So in order to minimize the sum of squares, all you have to do are to solve these equations, the linear equations, to make these terms 0. You have to do it in reverse order because this one has got all the variables in it. You've got to start at the far end and you get the values for your variables, and that solves the least squares problem. Okay, it has nothing to do with matrices. It's not the way that Legendre solved it. It's an ingenious way to do it because you can see, obviously, I'm minimizing the sum of squares. The way it's taught now, it's just, oh, you got to believe all this linear algebra and everything. But here, I mean, that's the sum of squares and you're minimizing it. Clear, done. Okay, so when Gauss did Gaussian elimination, this is the way he did it. All you have to do are know the values of these bracket things. You don't have to have symbolic algebra. You don't have to have any more equations or any more elimination. You just, here, remember, these are what the formulas are. First you compute all the single bracket guys, then you compute the first ones, and then the second ones, and then the third one. So he just wrote down all these numbers in columns. And the beauty of this was that it allowed you to just do the important thing, which was the arithmetic, once you know that the problem is going to be solved. And he likely evaluated these things using logarithms. There's something called a Gauss logarithm that allows you to do subtraction, but I can't actually say that he did that. I wasn't able to find any evidence or comment on it, but it seems likely that's what he did. So here he was actually in this one solving an orbital problem, and in there you have, I think, 6 or 7 variables, and so that's why he stops at 6, because it's 6 unknowns, 6 parameters in the problem. Okay, now there's another least squares problem that was actually the important one. So Gauss was at the University of Göttingen. He was very famous for this least squares calculation, but he needed a way to support himself, and so he got a grant from the local duke or whatever to make a map of the part of Germany that surrounds Göttingen. This is what maps looked like in those days. This is of Holland. Gauss would have kind of lived over here nearby in Germany. And so they would build all these triangles, and then once you measure the angles, then you can build the triangulation on a sheet of paper and you can draw the map. Okay, the problem is that the measured angles are inconsistent. So before you can use them, you have to adjust the angles. And what you have are a lot more angles than you have conditions they need to satisfy. You know, you have to have that the sum of the angles in a triangle is 180, And Gauss knew about the curvature of the Earth, so it's a little bit bigger than 180, but he was Gauss, he knew about that stuff. And the sum of the angles around the vertex is 360. So in this one little problem he solved, he's got 27 angles and 13 conditions. So that gives rise to a underdetermined system of equations. Here's the 13 conditions, and he wants to solve for the smallest solution that satisfies those 13 conditions. The original least squares problem was this one, and that's the one that Legendre invented and that Gauss used for orbital calculations. But in Gauss's day, the important one was this one, because this is the one you use to make maps, and governments would pay for maps, okay? Napoleon wanted to invade you, he needed a map. Okay, that's why the French had very good map makers, because that was what was one of the keys to Napoleon's success. A lot of people wrote textbooks about this stuff. Chauvenet was a prominent American mathematician, and he wrote a long book about astronomical calculations, and in particular, he would describe these methods that Gauss used, these kinds of bracket calculations. Okay, so before we get into the actual professional computing, and now is the time when you have to think about, are you really going to stay to the end of this talk, because we're about halfway through now, a little bit more, and I'm just finishing with Gauss. Here's the important thing for your careers that you will see happening in the next 100 years of this story. You got an important calculation, and it depends on 4 things. It's got to be useful to society. Okay, it's not pure math. There's got to be some math formulation. In Gauss's case, it was something called the adjustment of observations. That was a main piece of the mathematics curriculum in the 19th century. You got to have a technology for computing, and you got an algorithm that exploits the technology to solve the problem. So here's Gauss invented his brackets. Okay, but what happens is that technology moves forward, and the algorithms change, or the impact change, and then the algorithm has to keep up. And when you get to be my age in your careers, you will see that this happens to you as well. That everybody has a way to compute something, and 10 years later it's completely different. When I started, the big thing was to write code for vector computers. Okay, who has a vector computer today, right? So everything, you will see here in this history of Gaussian elimination that everything changed several times. The first change was Doolittle. So Doolittle worked at the US Coast and Geodetic Survey. So this was one of 2 agencies of the American government that made maps, and they specialized in the coast, actually. And this was their building in Washington, and there's the Capitol. So again, the impact is still map making. The math is still Gauss's adjustment of observations. But for Doolittle, the technology changed. He was going to use multiplication tables in order to make the arithmetic fast. And so he invented Doolittle's method. Now this is what a professional multiplication table looked like. This is the Krell's tables, and so this is the number 124, and these are all the products of 124 with other 3-digit numbers. So you go up here, 124 times 305. You go across, the first 3 digits are 378, and then you have to get the last 2 digits somewhere, and I guess that's them right there. Maybe I've got that backwards, I'm not sure. And looks like he only got down to 339, so there must have been another page after that to contain the rest of the numbers. But the advantage of this table was you could turn it to one page, and there you had all the multiplies done for you, so long as you were happy with 3 digits. Okay. So Doolittle organized the calculation to put all the multiplies kind of like together in one spot. So first thing you have to do is you've got like coefficients of your variables, and you're going to have to divide by this one. So somewhere you get the reciprocal, and then you're going to multiply this reciprocal by all these other numbers. So okay, so if this is 124, You just go to the table, and whatever all the other numbers are, the blue numbers, you can just look them up on that one page. So it's really quick to do this. Then there was another table he had where he would actually do the addition and the elimination step. And again, he arranged it so that he's got the same multiplier that's applied again and again to all the numbers. So he could again refer to one page in the table to do the multiplies, and then he had to do the subtractions by hand, I guess, unfortunately. So Doolittle was really good at this. Okay, he actual documented, published in American government publications, if you can believe those. He could solve a 41 by 41 system of equations in a week. All right, and I challenge you to do 5 by 5 in a week, you know, if you're doing it by hand. He was able to do this for two reasons. First, he had this very careful plan. All his tables worked out. It took me a lot of work to figure the tables out. And then he used the multiplication tables of Kraut to do the arithmetic. Now, his livelihood depended on being the only person in the federal government of the United States who could do this well. Okay, so he was not about to teach some young guy to do his stuff. So the only reason he published a paper on it was because the superintendent of the Coast and Geodetic Survey said, "You will write this up and we will publish it." But in his paper, he held back certain important things. First one is, he comments that he needs iterative refinement because he's only doing 3-digit arithmetic. I mean, imagine a 41 by 41 system with only 3 digits. And then secondly, these cartographic problems they were sparse. And so he makes some comment about you want to take advantage of the zeros, and he's got a way to do that, but he never explained what it was. And that was, he wasn't about really he did what the superintendent asked him to do, but he didn't really explain enough to be able to repeat it. And you know, you can look in any SciAm journal today and you read these papers and you think, what the heck are they doing? You know, well, that's exactly the same thing. They're not really going to tell you. Okay, so I'm just going to go a little bit ahead of Kraut because he survived a change. Remember, there's the 4 things that make a successful calculation. Kraut was working on map making, or rather Doolittle was, but he survived a shift and his algorithm transitioned into statistical computing. And so here's a condensed form of his tables with the A part and the B part. And this was used for correlation calculations and regression calculations. So that was one of the examples where an algorithm transitioned from one problem area to another. Cholesky, of course, is a famous name. Again, he was working in cartography like Doolittle was. The math was the same. It was still Gauss's adjustment of observations. The technology, though, was completely different. Okay, this was the first personal computer, the first thing that you could really manufacture in large quantities. It was, you know, fairly inexpensive it was expensive, but I mean, at least you could afford it. It was invented by a man named Vilgot Odhner, who was a Swedish man who worked in St. Petersburg for the Nobel Company. And lots of these were manufactured. It's called a pinwheel calculator because of the technology in it. And Cholesky devised a method to use these pinwheel calculators to do the least squares problem. I think it's really fascinating how these things work. I'm not going to tell you how that is. Suffice it to say is that they had an accumulator here that could accumulate long multiplication. And if you didn't clear the accumulator, then you would just add the next product to the ones you already had. So you could accumulate sums of products on this thing, and that was the key. So I don't know how Cholesky arrived at his scheme because he didn't have matrices. Okay, all he had was this kind of description coming from Gauss and Doolittle. So this was the problem that you wanted to solve, this minimum norm problem with linear constraints. And the way Gauss would do it is to form the normal equations, solve them, and then you would have to evaluate A transpose the solution to get the solution of your original minimum norm problem. These are called the correlate equations. So what Cholesky did was he observed that a lot of matrices or a lot of problems have the same normal equations. So he wanted to find a problem with the same normal equations, but easier to solve. And so he said, look, I just discovered I can find a square matrix L. I'm using our terminology here because it's kind of hard to, it would be very verbose if I don't use some matrix terminology. He's going to find an L so that he gets the same normal equations. And then instead of this problem, he solves this one, okay? But the conditions, it's lower triangular square, there's only one solution, so forget the minimization, you've just got to find the solution of your condition and you've solved the problem. So all he had to do was solve this, he's got x prime, then he used the correlate equations to get u, it's the same u as down here, and then he gets x. So that must have been something about Cholesky's reasoning. The way the calculation was actually done was he would write the half of the normal equations up here, and then he would put in the coefficients that he was calculating in the lower half. And the formula for the coefficient was just all, inner product calculations, and it could be done on this. The story is that he was in the military and they actually used conscripts or people who were prisoners to actually do the calculations. I don't know if that's true or not. A man in France has written a long biography of Cholesky, and you might learn more about that. So now the problem with Cholesky is he's a little bit like the ancient Chinese, the ancient math, the ancient Chinese, which is if it happens but nobody knows about it, did it really happen? If there's no connection from what happened in the past till today, the methods we're using don't necessarily follow from what happened in the past, even if it was very interesting that they were able to do it. So what happened with Cholesky was that his stuff was only published in a geodetic, he died in the First World War, and then his calculation method was only published once by a friend of his in a geodetic journal. And apparently, Cholesky's method was used by French and Scandinavian geodesists to do these map problems, but unclear how much it spread beyond that. What we call Cholesky's method was discovered by a man named Dwyer in the United States. He was a statistician at the University of Michigan, and it was widely used, Dwyer's method, called the square root method, in the United States. And then somewhere along the way, somebody said, oh, this was actually done by Cholesky 50 years ago, and so then the name got changed to Cholesky. Except the people who renamed it were British, and the British always like to change the final Y on a Polish name to an I. So you can always tell when this naming tradition started or propagates in the literature because it's called Cholesky with an I, even though he was really Cholesky with a Y. But that's neither here nor there. So Cholesky, it was very nice what he did, and it may be important, but it's hard to say that it actually impacted what we do today because the actual calculation was rediscovered independent. The last person I'm going to talk about is Kraut. He's a little bit older than the ones or more recent than the ones that I've mentioned here, but he's the last of the hand calculator algorithms. So this is Kraut. He was a professor at MIT. The reason he looks kind of beefy is because he was a baseball player as well. And what happened here was that the social impact changed from cartography to electrical engineering. So in the 20th century, starting after World War I, there was a big emphasis on having scientific engineering, science-based, calculation-based type of engineering designs. And so Kraut was part of that at MIT. And he worked on, in particular, calculations for EE and Kirchhoff's laws, linear circuit analysis. And this is pretty much like Cholesky. He's using calculators, except by now they were electromechanical. This was the Marchant, it was the Porsche of calculators. It was the iPhone 6. It was the best thing. And it was built right here in the Bay Area. It was built, they had a factory on San Pablo Avenue, just south of Berkeley in Oakland. So Kraut's method is, okay, now I'm officially over time. Everybody realizes that. So Kraut's method was another one of a little bit like Cholesky's, because you wanted to make it as compact as possible. So you would write down your equations. The original variables would be the a's, and the right-hand side would be the b's. And then what you would do is you would kind of do this bordering algorithm where you would deal with everything that I've got blue here, and then you would go down and we deal with that, and pretty soon you've used up your whole array. So I've never seen it done this way before. You know, usually the bordering algorithms, they add rows and columns, but instead he's taking rows and columns away. And it was a very simple rule. Basically, if you want to update this guy, you just subtract off the inner product of the two red ones here and the two red ones up there. And then depending upon where he is in the U or the L, you either divide by the diagonal or you don't. So that was the whole algorithm. Okay, it was very compact. And on a machine like this, it worked really fast. This was an ingenious machine. It could do the arithmetic as quickly as you could type it in, and it was all mechanical. The problem, and well, let's see, so his idea was picked up by the Marchant company. They would distribute something called Marchant methods that would come with their machines and tell you how to use them for various calculations. So it became instantly very widely known in the United States. But there was one critical flaw with this, okay? He was doing double E. He wasn't solving linear equation, least squares problems anymore. So they weren't normal equations, and there's no way to reorder in this scheme. So, you know, pretty much it'll work, all right? But maybe every once in a while you run up in a problem. You get the calculations work out, but the answers is completely garbage. So it was Kraut's method that led to this belief that Gaussian elimination is somehow inherently an unstable algorithm. And it is. Eventually they figured out you absolutely have to reorder, and then you're probably going to be safe. And so this was a useful algorithm, but it was kind of, unfortunately, didn't allow you to do the reordering. All right, so I'm going to now talk about the matrix interpretations, which is the last of the three phases. And so this is probably what's most familiar to people here. It's also the last stuff that was invented. And for most of its existence, it was not really useful. It was kind of like pure math for calculating. Matrices were invented in the 1800s, in the 19th century, but they were a creature of pure mathematics. Arthur Cayley was one of the inventors. There were about half a dozen other mathematicians who worked on matrices. There was lots of papers about the inventors of matrices. But they weren't actually used in practical calculations. There was, I mean, what could you do? A matrix multiply? You know, give me a break. It's just not useful to know that. It's nice theory maybe, but not useful for calculating. After computers were invented, matrix multiplication, it's just a do loop on the subscripts, right? So then matrix calculations transitioned directly into computer programs. But for the first part of its existence, it was kind of like pure math. So the people who brought matrices into the engineering kind of computing world were first this man here. He was an astronomer in Warsaw. I'm not going to try to pronounce his first name. Banaszewicz was his last name. And he was the last inventor of matrices, but he invented them a little bit differently than everybody else. He called them Krakowians, and after Krakow. And the problem was that he multiplied column by column instead of column by row. And that was the right way to do it if you want to do hand calculating, because you just go down the columns, and you know, otherwise you got to do this guy, and it's a little bit hard to organize. But if you're doing column by column, it's easier. And in the context of Krakowians, he invented Schur complements and Cholesky's decomposition and all that. Okay, it's hard to say that anybody used these methods except maybe other people in Poland. But we'll see that he did have a role to play, so that's why I'm mentioning him. The other important people were 3 British engineers. They were a lot more than engineers. They were graduates of Cambridge. They were advanced graduates. They became members of the Royal Society. So these were important engineers in England. They worked at the NPL. And they wrote a book called Elementary Matrices. And in it, they described how you could use matrices to set up engineering analyses. And they talked about operations on matrices. And their idea of an operation was like a row operation or a column operation. Okay. And unfortunately, the title of their book meant this is an elementary book about matrices. But that word elementary was used to describe these kinds of row and column operations. And so today, the multipliers that give you row and column operations are called elementary matrices. But it's all a mistake. It really wasn't meant that you should call them Fraser matrices or whatever. An elementary matrix is a diagonal plus a dense row or column. Also, some people figured, oh, but these are the things you need to do Gaussian elimination. Let's name them Gauss transformation matrices. Wrong. Okay, Gauss didn't know what a matrix was. And he didn't solve non-symmetric problems. Okay, so the advantage of the matrix formalism was that all these people who invented algorithms that didn't have matrices, you could all of a sudden express them very simply in matrix form. But somebody had to figure this out. And there were really 2, maybe 3 groups of people who did that. A Danish geodesist named Jensen wrote a book in which he being in Northern Europe, knew about Banishevitz and had seen him give lectures on his work. And he read Fraser, Duncan, and Coller's book. And so he decided to express the Gauss calculation with the square brackets and all that, and Cholesky's calculation in terms of matrices. And so he was the first one to really say, oh, this is just a matrix decomposition. It has a matrix interpretation. And in his paper, he actually had these little pictograms. 2 triangles gives you a square. The other one, we saw Dwyer before. He was a statistician at Michigan. He showed that Doolittle's method produced triangular matrices. And remember, Doolittle's method had transitioned into statistics, so that's why Dwyer would have been interested in that. And Dwyer also was the man who invented what he called a square root method, which now we call Cholesky's method. I did a citation analysis of all the people before 1950 who wrote books that contain matrix decompositions to see who really came up with it. And I concluded that the people who didn't cite other people or cited them but for the critical idea were guys like Banishevitz, Jensen had, came up with it, Dwyer. This man here seems to be an outlier, but he had some good ideas. And then von Neumann and Goldstein. So a lot of other people worked in this, like Wilkinson. He was at the NPL. He learned about matrix decompositions from Fraser, Duncan, and Coller. But apparently the original ideas were with these few people here. Von Neumann and Goldstein, forget about this. In their analysis of Gaussian elimination, they took the school book version of elimination and they interpreted it as a matrix decomposition. And they were the ones who came up with the LDU form, the triple product with the diagonal out separately, except they called it CDB, which was really a bad choice of letters. And then just quickly, what happened after that was this man Todd, whom I don't know if anybody here ever met him. I corresponded with him. He was a really interesting fellow. And he gave a series of lectures in England in 1946 in which he introduced British mathematicians to the work of Cholesky. And one of the people attending his class was Leslie Fox, who picked up matrix decomposition from Todd through this way, and then he took it back to his colleagues at the NPL who would have been Turing and Wilkinson. That's probably where they learned about matrix decomposition. Turing I mean, he's a genius and all that. I can't say he invented anything new about Gaussian elimination, but he had a way of describing things that made it just crystal clear, and you said, oh wow, that's a really neat idea, I'm going to go out and think about that. So he took the idea of starting with the kind of elimination you would learn in a school book, and then using these elementary matrices of Fraser, Duncan, and Collar, which Jensen had used, and describing exactly how you reduce a matrix as a product of elementary matrices. And then Fox picked up Turing's, Turing only wrote one paper on this. Fox and Forsythe and Moeller picked it up. Okay, so that's the history. Now, why is it called Gaussian elimination? I'm almost done. Why? Well, it was sort of a mistake. It was never meant to be called Gaussian elimination. Remember, Newton called it extermination. If you look at all these, I looked at all these old books in writing my paper. Euler called it the most natural way to do things. Legendre called it ordinary method. Gauss called it vulgarum eliminatorum, common, vulgar meant common, so just common elimination. The Frenchman Lacroix, I always find it odd to rely on somebody from New Zealand for French pronunciation, but since I never studied,
3 years of French.
3 years, and you certainly remembered it. So he was the one who finally named it elimination, so Newton's terminology kind of died out from European textbooks. And then there were lots of people who basically called it some form of elimination. Occasionally they would reference Gauss, but usually that was because they were using his angle bracket notation and that very specific algorithm he had for elimination of symmetric matrices. And then finally, some people started calling it Gauss's elimination process, but Stanford's Forsythe in 1953 wrote a paper for the Math Monthly, I think it was, and he talked about the history of elimination, and he made some comments that the thing you learned in high school algebra was really described by Gauss. Okay, now that's absolutely not true. He didn't know what he was talking about. I know he's a famous Stanford guy, but he didn't know the history. But anyway, Forsythe associated it with Gauss in the modern post-World War II mind. And then after that, he called it Gaussian elimination. Householder picked it up. Wilkinson called it Gaussian elimination. And so it was sort of, it was by that point attributed to Gauss. So that's what I have to say. There's a much simpler description of all this in the notices of the AMS, and here's the first page of that. Thank you so much for your time.
Thanks so much, Joe. It's truly fascinating facts there. Before questions, let me mention we have the honour of having Professor Don Knuth among us, and his amazing texts, well, books certainly cover a lot of history, but certainly have a question.
I have a simple question. When you're talking about the Chinese version, you mentioned the phrase Gauss-Jordan elimination. Can you elaborate? Then you mentioned Jordan 1895 or something. Can you elaborate on that a little?
There are a lot of people named Jordan, so I'm not
I'm thinking of Wilhelm Jordan.
Wilhelm Jordan was the man who wrote, I think, a German textbook on geodetic calculations and geodesy. And he probably had a lot to do. I think this book is still in print in some form. It continues as a textbook today. And so I'm not sure if he originated that method, but there was a version of Gaussian elimination where instead of reducing it to lower triangular form, you reduce it to diagonal form. And so by Gauss-Jordan, I mean that version. And the critical point there is that you create zeros as many as you can, as early as you can. So you clear out the first column of zeros below the diagonal, and then the second column you do zeros everywhere except the diagonal, and so on down the line. Whereas the Chinese, they reduced it to triangular form, and then once they had the last little row with a single number in it, then they were able to introduce zeros above the diagonal. And so it saves computing time because you don't operate on these entire rows. Yes, sir?
So then what do you recommend that we call it? Newtonian extermination? Or
I remember speaking to someone, and the funny thing is that you've got, Newton is responsible for two really critical algorithms, right? There's Gaussian elimination, and there's Newton's method for the nonlinear problems. And you kind of think, maybe he did encounter all these different things in his work. He was the first real great mathematician who worked as a scientist. I think you should name it after Gauss, because even though he didn't invent it, he was the one who created the first professional method, and it was from him that people learned you could devise the algorithm to match your workflow. And so he was kind of like the first programmer or numerical analyst in a sense, in that sense.
Likewise, what do you think we should call identity plus rank 1 matrices? I always call them elementary.
Elementary matrices.
That's false.
It's really odd how these names come up. Gauss transform, I don't know what to call those things. I mean, I think elementary is probably pretty good, but it's just interesting to note that it didn't really mean what you think it means. It's not a simple matrix. It just appeared in a book that was an easy introduction to matrices. Yes, sir?
Well, as you mentioned, many of these guys were interested in the nonlinear problems. In fact, the orbit problem is a nonlinear dispersed problem. And curiously enough, even in the 60s, the astronomers called the method they use, which is the method of differential corrections.
Uh-huh.
And I learned later to use it under that name, and then I learned later that was linearized least squares.
I see, yeah. Well, what Victor refers to, I think, is something that you really have to be aware of. I kind of gave a Jean Golub history here, which is the idea that numerical methods kind of exist separately as a branch of pure mathematics, and you just go off and invent your best algorithm. But what actually happens is that most of the algorithms are embedded in some technology, like least squares for cartography or least squares for astronomy or something like that. And to really find an area to make an impact in, unfortunately, my view is that it's, as you know, it's kind of been broken up into all these different technological fields, and you have to hunt for one where you can make an impact by devising an algorithm.
You may be interested to find that very few of the medieval books refer to linear equations at all. My recollection is that almost always they were talking about polynomials in one variable, and they had, they even had, they used one letter for x, another letter for x squared, and a third letter for x cubed. But there was only one variable. And you were solving for x, but you weren't, but there was one unusual Arabic text, I can't remember, I think it was Al-Samawal was his name, but he had an equation, he gave 1,000 linear equations in 20 variables, very overdetermined. But I think he just wanted to show, I don't really understand the idea, but essentially, he took different subsets of those variables and added them together.
Mm-hmm.
But I think he wrote it by just starting out and say, well, let A equal 1 and B equal 2 and C equals 1 and D equal 5, and then he's going to be very impressive by saying, now I can solve 1,000 equations.
I see.
He basically just starting with the left-hand side, and he figured out what the right-hand side had to be because he already knew the answer.
I'm just a little bit familiar with that text. I don't know why he did that. He had all these numbers and he took all combinations of 5s and added them up, and I'm not sure why he did that. But another thing I have to say is that a lot of the Arabic manuscripts have never been read. I mean, they got put away in libraries, or I guess the American Library, the Library of Congress supposedly has a lot of Arabic texts that have never been translated. Probably nobody's cracked them open for a long time. Be interesting to know more what the Arabic mathematicians were really doing. But the way the history is now is that, well, they kind of preserved all this stuff that came from the Greeks and the Romans and then shipped it up to Europe at some point, and then other additions were made there. But I don't, it can't be that simple, but I don't really know the story.
Was there another question here?
The Sumerian algorithm sounds a lot like iterative refinement, a 1-bit approximation and a 2-bit approximation. So I wonder if they doubled or just added.
So far as I know, they only solved 2x2 systems. They never went beyond that. But
remember that first they divided it in half.
Yeah.
And they would define sort of like increasing the precision.
Yeah, that's interesting. There in the literature on algebra, there's all this description of the sort of the regula falsa, which is you introduce a new variable and then you try to use that variable to describe your other conditions and obtain a condition for it, kind of like what Diophantus did. And I've seen some articles that said the Sumerians were sort of trending in that direction, but I don't know. There's very little written, or very little survives from the Sumerians, but a lot more than survives from, say, Egypt or India. So there's another problem where you go to the market. Did I mention this? You go to the market and you buy some fish from 2 different stores, and you spent this much money and you got this much fish, and you have the prices, and then how much did you buy from each store? So again, it's sort of interesting that the textbook problems are always made up. There can't be any reason why you would want to solve these problems. Yes, sir?
Was Doolittle the first case of iterative refinement being used?
I don't know where iterative refinement was first used. I suspect that Gauss knew about it, but I'm just guessing. I do know that Doolittle mentioned it. And it would be nice to do iterative refinement in MATLAB if you could only do quad precision residuals, but you cannot do quad.
Yeah. Joe, can I quickly mention, I had never heard of a Krakowian before, but there's another adjective from Krakow that Chopin wrote.
Interesting.
It's a fabulous piece. The last page is the most lively, sparkling tune you've ever heard.
Yeah.
Yes.
There is actually there is something called Krakowian algebra, which basically is, in modern languages, the matrix multiplication A times B transpose.
Yes.
It's not associative, but it has some interesting properties. It's actually
that comes from Banishevitz.
There's a book that I couldn't buy because it's like $300-400, but there is a book called Krakowian algebra.
Yeah,
Column by column?
it's the
aligned columns. You multiply matrices by columns the way that astronomers do.
Yeah, and the reason, so for the Krakowian method, Cholesky factorization is really L squared because the L transpose is L, and so it's kind of interesting now. But all that did come from Banishevitz, and I've seen the book you're talking about. It doesn't have history in it. It talks about his papers. He wrote lots of these papers. Most of them were published in the proceedings of the Polish Academy of Sciences in the 1930s. Hitler invaded on one side, Stalin invaded on the other side, and it's hard really to see how that had much impact beyond the 1930s. But he was ahead of his time there. And his work was picked up. It inspired Jensen.
He was ahead of his time in avoiding aging.
In what?
Avoiding aging.
Doing the column stuff. Yeah, exactly. Yeah, right.
Well, thanks so much for remaining interested in history for 90 minutes, I think.
Oh my gosh, yeah. Yeah.
Also, as you see, Joe's talk is recorded, so we're all part of history now. Thank you.